Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations. So as a quick recap, we said that in general, we want to solve a differential equation such as y prime equals f of x and y, right? And we said that this is the most general case for an ordinary differential equation or ODE. And then if the right hand side, the function doesn't depend on y, so y prime is just f of x and x is the variable, then the problem is just doing a numerical integration, right? So that doesn't have any challenge, we already know how to do it. But then we said that in general, in order to solve y prime equals f of x and y, we need to have initial condition, which is also called IC, initial condition. And typically it's given as a point for x, and it's mostly x equals 0. But here we can have anything like x equals a. So y of a is given. Sometimes instead of initial condition, we have final condition, y of b equals yb. So in general, in order to be able to solve the differential equation, we have to know the value of the function at some point. And based on that, we can find the value of the function at the later points or earlier points, right? Both are possible. And we said that the common numerical approaches, the very basic one is Euler method, forward Euler method, and then backward Euler method, midpoint method, RungeKutta method. And in particular, we talked about RungeKutta fourth order. And later we will talk about the general family of the RungeKutta, which also includes Cash-Karp method and Fehlberg method. And we said that most likely we always end up using RK4, RungeKutta fourth order, but in general the stability of the solution depends on the ODE itself, depends on the actual equation for the ODE, all right? And sometimes it's better to use backward Euler method. It has more stability than the forward Euler method, but then it adds more computation costs. So explicit methods such as Euler method, forward Euler method, or RungeKutta RK4 are typically used because they are explicit, so they can easily give you the values of the function at the later points. All right. And we said that in general the idea here is that at each point x, we can estimate the value of the function at some very small point next to it, x plus h. And the Euler method, the forward Euler method, is just estimating y prime based on a simple forward difference. And then we said that the key point is that in order to start from point x equals a, which y of a is given, the initial point is given, and in order to find the value of the function at the later point b, we create a sequence of the values of the function that converges to the value of the function at point B. And the way we create this sequence, yn, is by basically discretizing the interval between a and b into n sub-intervals. And we always go for uniform partitioning in this case, because non-uniform partitioning or quadrature partitioning has more complicated equations. So we just prefer to do uniform partitioning, all right? And then we build the y and x at each point. X is just by adding the h to the previous x because it's uniform partitioning. And then y, for Euler method, we just evaluate the f at xi, yi, and then we get yi plus 1, right? And then the key here is that this sequence converges to the exact value of the solution, right? And we said that therefore the way we do it, we first create a sequence object, and based on the method that we choose, for example here Euler method, we create a sequence that converges to the value of the solution at some point, let's say x1 or b, right? And basically n here in this lambda expression, n is the number of sub-intervals from a to b. And this for loop just generates the sequence, right? And then we said that the beauty here is that this becomes a general approach. So instead of having Euler sequence, we can have RungeKutta sequence, we can have midpoint sequence, we can have Cash-Karp sequence, whatever. The only thing that changes is this for loop, the way we generate the yn sequence. That's the only thing that changes in our implementation in Java. Everything else is exactly the same. And that's very beautiful, because not only it makes the implementation much easier to understand, also because now that we have a sequence and we're looking for the limit, we can use sequence acceleration. And in this case, we should use Richardson acceleration. And we prove this by just looking at the Euler itself, and we said that it has a painfully slow convergence. But once we apply third order or fourth order Richardson acceleration, we see that the convergence becomes very fast, all right? And then we said that in order to avoid the error at a very far points from the initial point, we can use the previously calculated solutions, the previously calculated points, as the new initial point for finding the solution at the later point, right? And we prove this point by looking at one of the important equations, which has an exponential solution. And it turns out that the exponential solutions, y prime equals some number times y, is actually a measure of the stability of a differential equation, a first order differential equation. We will talk about this later, because in general exponential functions have the fastest growing or fastest decaying behavior in any natural physical system, right? So if the solution doesn't have much error for exponential solutions, then we can be confident that the numerical methods are stable. And then we looked at more examples of the Euler method. Here I'm comparing the exact solution with the Euler plus fourth order Richardson acceleration. Then from Euler we said that it has a very poor order of error. That's why we have to use convergence acceleration. But then now we said that we can actually improve the error by making a better estimation of the y prime, right? And we said that one way is to look at the midpoint method, and that basically says that, okay, the slope of the secant line must be equal to the slope of the tangent line at some point inside the interval xn and xn plus 1. And obviously the reasonable choice is to approximate this point with the midpoint of the interval. So yn plus 1 is yn plus h times f of xn plus half yn plus half. So xn plus half we can exactly calculate it. Yn plus half, we don't know the value of the solution at midpoint, so we estimate it with the Euler method. So yn plus h over 2, because now from xn to cn, if cn is the midpoint, the step size is h over 2 times f of xn yn. All right, this is how we constructed the midpoint method. And we said that this has, on a uniform partitioning, it has 1 over n squared error or h squared error, which is 1 order of magnitude better than the Euler. But obviously the price that we are paying is evaluating the function f of x and y at twice, right? We're evaluating function twice, and that's the general trade-off in general for solving differential equations, ordinary differential equations in this case, is that we are trading the accuracy with the number of times we need to evaluate the function. And then we said that we can extend this way of thinking about increasing the accuracy of the solution by going to higher order approximations, and the famous one is runge-kutta fourth order, okay? And it creates a sequence yn plus 1, which is yn plus 1 over 6, k1, 2k2, 2k3, k4. And again, uniform partitioning, and k1, k2, k3, k4 are given by these equations. And so for the fourth order runge-kutta, that gives us a h to the fourth error. So it's a fourth order error. We have to evaluate 4 times, all right? So for Euler, the error is order h, and we evaluate 1 time. For the midpoint, the error is order h squared, we evaluate twice. For RK4, the error is fourth order, and we are evaluating 4 times. Now it turns out that after RK4, if we are trying to find order of h to the fifth order error, we have to at least do 6 evaluations of the function, not 5. It's not possible to do 5 evaluations. And we'll discuss this in more details when we talk about the general runge-kutta family. That's why the RK4 is always considered the sweet spot, because it gives you the fourth order error with the minimum possible evaluation, which is 4 times. So if I evaluate the function 5 times, I still get a fourth order error, not a fifth order error. For a fifth order error, I have to evaluate the function 6 times, not 5 times, okay? And we said that the interesting thing is that if the right hand side, the function f of x and y, does not depend on y, then the runge-kutta fourth order becomes the Simpson's method for integration, which we discussed in details when we talked about numerical integration. And again, to reiterate, for numerical integration, if y prime is just equal to f of x, we always prefer quadrature methods that operate based on a non-uniform partitioning of the interval, because they always have better than linear convergence. They have a superlinear or quadratic convergence, unlike uniform partitioning that can never have anything better than sublinear convergence. And the same thing for runge-kutta. We said that we create this sequence of functions by partitioning the interval between a and b. A is our initial point, b is the point that we are trying to find the solution. And then we don't even need to do any Richardson acceleration. We can create the RungeKutta sequence easily by, again, the code is exactly the same as Euler and Midpoint. We just change this implementation inside this for loop that generates this sequence yn, okay? So we calculate k1, k2, k3, k4, and y is y plus k1, 2k2, 2k3, k4 over 6. And we start from y0, x0, and then becomes y1, x1, y2, x2, and etc. Eventually it returns yn, and this is a multi-line lambda expression, all right? And then we said that the RungeKutta method does in fact have a very fast convergence, and we took n equals 20 as the stop point for RK4, all right? And then the same thing here with evaluating over a very large interval. We take the previous points as the initial points for the next point that we evaluate when we pass in an array of x values to solve the solution, all right? And then we said that now we want to, most of the time we have a system of first order differential equations that are coupled together, and this is the general format of the first order system, right? y1 prime, y2 prime, ym prime. So we have m equations, and these are equal to f1 of x, y1, y2 to ym. So x is the variable, y1, y2, and ym are functions, real functions, the functions that have real value, right? And the goal is to find y1 all the way to ym, and we have m equations. We cannot have less than that, and if we have more than that, we cannot have a unique solution. And in order to find a unique solution, not only we should have exactly m equations, but we also need to have m initial conditions, all right? y1 at x0, y2 at x0, and ym at x0. And the general approach was to use any method and define a sequence that converges to the value of all the functions at the given point, and then we do acceleration or whatever we need. And again, in order to make life much easy in terms of the implementation, we went with a vector-based approach or an array-based approach, and we said that for all the previous methods, Euler, Midpoint, RungeKutta, that basically generates a sequence. The sequence is still valid for a vector, right? Each vector represents one of the functions, y1, y2, each component of the vector, right? So we have a y vector. A y vector is equal to y1, y2, ym, all right? And in order to do that, we implemented an object called nd array, and this array is basically encapsulates a typical double array with the support for operator overloading. And the reason we did that because we wanted to avoid writing a lot of for loops and whatever. It's just much easier to have an array object that already supports operator overloading, all right? And then we also defined a vector-based or array-based sequence. Array sequence is basically when we evaluate it, it returns an array, nd array, And if we want to get the sequence for a particular component of this array sequence, we use a lambda expression that represents a sequence. So we evaluate at n, which returns an ND array, and we just call the whatever index we're looking at, all right, for this array. And as you can see, we create our array func. So this is a basically this function represents the this vector, this array, right? So this function returns an n-dimensional array, right? Takes x and all the y values, and then we create the Euler sequence, and then this way. And we showed that this method works very well. And here I'm using fourth order runge-kutta. And then we looked at many examples, like oscillatory example. And again, to note that so far all these functions are assumed to be real functions. They have real values. They don't have a complex value, all right? And then we said that actually one of the very nice use cases of the way we are solving a system of first order differential equations is that we can actually use it to solve a higher order differential equation, a higher order linear differential equation. And we said that by linear, it has to be linear in the highest order derivative. It doesn't have to be linear in, here for example, we have y double prime, y prime, and y. It has to be linear in the y double prime. It could be y prime squared or y squared, doesn't matter. And we said that we do a change of variable and convert this, for example, second order differential equation into a system of two first order differential equations. And the beauty is that when we do this and solve the system of differential equations, not only it gives us the value of the y, it also gives us the value of y prime. And then based on an algebraic equation, we can also find the value of y double prime. So this way of solving higher order differential equations allows us to immediately find y prime, and y double prime. And we had examples, for example, a free falling ball, a mass spring system that gives us a second order differential equations, and an electric circuit, RLC. And then the next question is that, okay, so far we have looked at the equations for which all of the functions, for example, if you look at this y prime equals f of x and y was a real function. X is a real variable and y is a real function. Now the question is, in most situations in physical systems, we have a complex function that has an amplitude or phase, or a real part and imaginary part that is in fact describing the state of the system. So it's not a real function, it's a complex function. So far our variable and functions were real valued. In most cases the variable is real, so the variable is real, but the functions are complex. And this happens all the time in physics, in mechanics, in electrodynamics, in quantum mechanics, all the time. So complex functions represent the phasors of a sine or cosine function. So the phasor, what do we mean by phasor? So if you look at the general representation of a cosine or a sine function, a general representation is that if I have the cosine function, it could be an amplitude times cosine of omega t. Let's say t is our variable, or x. Typically it's t. In physics, t represents time. So this is more like the oscillation in time. So t is the variable, omega is the frequency, and then some phi, some phase, right? This is the most general case of a cosine or sine function. And this can be very well described by the amplitude and the phase. So this a times cosine of omega t plus phi equals to real part of a complex function, a e to the j phi e to the j omega t. And the phasor is defined based on the complex amplitude and phase. F, the phasor f, is equal to a times e to the j phi. So if this is the phasor, you see there is no time dependence in the phasor. So f of t, the real value the real value, the time dependent function is real part of the phasor, the static phasor. It doesn't have any time dependence, times e to the j omega t, which represents the oscillation. That's the definition of phasor. So one-dimensional ODE in a finite interval a and b, again, it's y prime equals f of x and y, but now y is complex. And the initial condition y of a is y0. Now y0 is complex. Y0 is complex. Is a complex number. All right? So have this in mind. Y of x is a complex number. X is real. So we are still assuming that our variable is real. F of x and y. So in general, f of x and y, x is real, y complex. So f of x and y is in general a complex number, a complex valued function. So how do we solve this? So the way we're going to solve this, we're going to build based on what we have built so far in terms of solving ODEs. We can solve a real valued ODE. We can solve a system of real valued ODEs. So it turns out that if I write y of x in terms of its real and imaginary parts, so because any complex number, any complex function can be written in terms of a real function plus j times another real function, right? U and v are real functions. U represents the real part of y of x and v of x represents the imaginary part. I can always do this. Now take this and put it in the y prime equals f of x and y. And note that we can also write the f of x and y in terms of its real and imaginary parts. So f of x and y is f sub r, f real of x, u and v, right? And j times f imaginary, x, u and v. So if we do this, we can say that, okay, when two complex numbers are equal, the real part must be equal to the real part and the imaginary part must be equal to the imaginary part. So both conditions should be satisfied simultaneously. That's why if I put u plus jv on the left side, I get u prime plus jv prime. On the right side, I get f of r plus j f sub I. So u prime must be f sub r, the real part of x u v. V prime must be f imaginary x u v. Now we have a system of two real valued ODEs, u and v, and f of r, f sub r, and f sub I. And we already know how to solve this, right? So a complex valued ODE with a real valued variable. Remember, the variable is real. If the variable is complex, things get way complicated because functions of complex variables behave quite completely differently from functions of real variables. Okay, so here we are still assuming that the variable is real. A complex valued ODE is a coupled real valued ODE system. That's the baseline. That's the conclusion here. And we already know how to solve this system of two equations, right, for real valued functions. So the problem has been already solved. We have already solved the problem of solving complex ODE of complex functions. The only step here, the only extra step is to convert the original equation y prime equals f of x and y into the system of equations u prime equals f sub r and v prime equals f sub I. That's the extra step, right? And that's what we're going to do. So I'm going to define an interface, derive function complex, and it returns a complex value. So this represents our complex function f of x and y. X is real, it's a double value, and y is a complex valued function, right? So x real, y complex, and returns a complex value. And then we define our ODE solver complex class. So this solves an ODE system, ODE equation, y prime equals f of x and y. Y and x are both complex. We pass in our f of x and y, which is complex. We pass in our initial value for x, and we pass our complex initial value for y. All right. Now all we have to do internally is to define an ODE system solver and a derive n function. So remember, derive n function, this was used for solving a system of real valued ODEs, right? So we have this function complex x0 y0, and then this func system represents the derive n function for basically the system of real valued ODEs, the u prime and v prime, right? So it takes x, which is real, z, which is an array of two variables, u and v, or z0 and z1. So z0 is the real part, u, z1 is the imaginary part, or v, okay? So z0 is u, z1 is the imaginary part, and v. So what I'm going to do here, I'm going to call the function, this complex function, passing x and y. What is y? Y is u plus jv. So z0 plus jz1, all right? And this returns the value of on the right hand side, this one, okay? And then my equations are the real part of this function and the imaginary part. So the function for the system of two ODEs is double val, this complex function, the real part, and val imaginary part, all right? And the system solver ODE, the ODE system solver has two equations, right? So we pass in our function system that represents the two differential equations, x0, and then we have to also break the complex initial condition into two real valued initial condition. So u is the real part of the y, so its initial condition is the real part of the initial condition of the y, right? So y0 dot real part, y0 dot imaginary part. And then we do a pass-through. Pass-through means now if I want to, now I can create an array sequence method, Euler sequence at some point, and we just call this ODE system solver and call the Euler sequence at this point. This returns a sequence that represents the u and v, and the values of this sequence must converge to the value of the u and v, the solutions, the real part and the imaginary part, all right? So let's look at some examples. Y prime equals minus y. We write y of x in terms of its real value, u of x plus j v of x, right? And then we put it on the both sides. The left hand side is u prime plus jv prime. The right hand side is minus u minus jv. So u prime is minus u, v prime is minus v. And what we see here is that there is no coupling actually between the real part and the imaginary part of y, right? Now let's look at another example. Y prime equals minus y squared. So left hand side is u prime plus jv prime. Right hand side is minus u plus jv squared, which is v squared minus u squared plus j minus 2uv. So in this case, the u prime is v squared minus u squared, v prime is minus 2uv. Now we see that there is actually a coupling between the real part and the imaginary part of the solution, okay? And in both cases, our approach works fine because no matter if there is a coupling or not, no coupling between the real part and imaginary part, our ODE system solver solves the system of u prime equals something, v prime equals something, and returns the solution, right? So our Java implementation is simple. We define the complex function f of x and y that represents the complex value of the right hand side. So it takes x as a real variable and y as a complex variable and returns a complex number. And then we define an ODE solver complex class, and all we do in this class is to transform the original problem into a system of two ordinary differential equations, right? And then we do a pass-through methods for solving, for example, Euler, runge-kutta, and they return array sequence or the solutions or whatever. So let's look at an example. So y prime equals minus y squared, and y of x is u of x plus j v of x. So u is the real part, v is the imaginary part. And the initial condition is given as y at 0 is equal 1 plus j, right? So in the past we had a real number here, but now we have a complex number here. And this differential equation has an exact solution. Y of x is 1 over x plus 0.5 times 1 minus j. So this is already a complex number. So the solution is 1 over x plus some complex number. If I put x equals 0, this becomes 1 over, basically 2 over 1 minus j, which is 1 plus j. So it satisfies the initial condition, and obviously you can confirm that it also satisfies the differential equation, which is very easy to see. So let's look at y at 1.5. So the initial point is 0. We're looking at a later point, 1.5, which is 0.470588, the real part, plus j times 0.117647, the imaginary part. Now we use our array sequence method here for the Euler sequence, and this returns sequences that converge to the real part of the solution and the imaginary part of the solution. Okay, so let's see what happens. As we expect for the Euler method, the convergence is painfully slow, but we definitely see the convergence, and they converge to the basically the actual or the exact solution. All right, so let's look at the code. We want to solve y prime equals minus y squared for complex function y. So y is a complex function, and it's only one differential equation, so we call our derivative function complex func, which represents takes a real variable x and a complex variable y, and returns the complex value of the right hand side, minus y squared. And this pov is coming from my complex math class. It's not coming from the math library of Java because y is a complex. All right, so minus y squared, and then the initial value for x is 0. The initial value for y is a complex number 1 plus j. And then the ODE solver complex, new ODE solver, we pass in the function, we pass in the initial value for x, the initial value for y, and then we create an array sequence yn that is basically it has two components. The first one represents the real part of the solution. The second component represents the imaginary part. So we take our ODE solver and call the Euler sequence at x equals 1.5. So we call the Euler method. It creates an array of sequences, two sequences that converge to the real part and imaginary part of the solution at 1.5. And then we create an array of indices, an array of complex functions that represent the basically the complex solutions. And then for int I equals 0, I less than length of the indices plus indices I is basically I, and then we calculate this sequence at I. It returns an ND array with two components, and the yn vals, the complex value, is the 0th component plus j, the 1 component. All right, and then we create the figure, passing the indices and the complex array. It already when we do this, it already plots the real part and the imaginary part separately. All right, and then yeah, so we see that definitely there is a convergence, and it's converging to the right values, but it's very slow. So we can do a runge-kutta fourth order, for example, and note that I'm using j by importing static members of the complex class from my mathlib library, and I'm using the pov, as I mentioned, from my complex math class in my mathlib library by importing the static methods in the complex math class. All right, because remember, y is a complex number, so you cannot use the power method in the Java's math library. You have to use a complex version of the power function. And here I'm plotting the solution from 0 to 20, all right? So 50 points, and we also evaluate the real part and imaginary part of the exact solution, and then we're doing the comparison. We're plotting the real part and imaginary part for the exact solution and the runge-kutta solution. And as you can see, our ODE solver complex, which basically breaks down the complex differential equation into a system of two real function ordinary differential equations, it works perfect, and it gives us the exact solution. All right, so this is the basic of calculating the or solving ODEs with complex functions. And it's very important because, again, in physics, in most cases we always have complex numbers, so we always end up with an ordinary differential equations that actually involve complex functions. Now, moreover, even the coefficients can be complex. So far, we've looked at the cases where the coefficients were real, right? But the coefficients could be complex, and our method still works because this derived function complex is general, right? It takes x, which is a real value, and y complex, and it returns a complex number. So it doesn't care about whether or not the coefficients on the right hand side are real or complex. They could be complex, doesn't matter. And in the next lectures, I will look at the examples that the right hand side of the equation is actually a complex, has complex coefficients. And we see that our method for solving the ODE of a complex function works perfectly. So I hope you enjoyed this lecture, and I'll see you in the next one.